So okay. Now I would like to continue with the topics that we talked about before the break, namely, so we calculated now the exact solution for pipe flow, as you can see here, and then we had a few other quantities that we calculated for it. There's one last comment that I would like to make that in black. One last comment is that kind of the general solution, as we have looked at, essentially has three different parts. One of them is a part that comes from, if you go here to the general solution up here, so we have three different parts. We have a part that is the parabolic part. We have another part. So we have a parabolic part, we have this logarithmic part, and then we have this this constant. So that means the general solution of uz as a function of r looks like this. We have minus dp, or I can use normal derivatives here. So dp dz times r squared divided by 4 mu, for instance. Then we have this a times ln of r, and then we have the term e. So what do these terms actually correspond to? Well, the first term here, the dp dz times r squared divided by 4 mu, this is a term that essentially comes from the influence of the pressure. So that means this is the term that is active if we have a pressure-driven flow. Pressure-driven flow, like a channel flow or a pipe flow. And this term, or the result of that, is essentially parabolic. Parabolic meaning this will give rise to a parabolic velocity profile because there's an r squared here. The second term that appears here for the pipe flow, but in a similar way it would also appear for channel flow, that is for all the parts that are shear driven. So that means when we kind of impose a certain shear in this velocity profile. Now for the pipe, this turns out to be a term that is logarithmic with r. In a channel, it would actually be linear for a Cartesian system. So a Couette flow, for instance, has a linear velocity profile. Well, so a shear-driven term, that would essentially end up with something that is logarithmic or linear in a Cartesian case. And then we have, of course, the last term, the b, that is then related to boundary conditions. What I want to say with that is that if you have combinations of flows where you have the walls moving and you have a pressure gradient on top of that, you would also get a combination of these different terms. And because these are all linear contributions, you would actually, you could use a superposition argument. So you could have, for instance, a channel flow where you have a pressure gradient and moving walls, then it will just be a linear superposition of the pressure driven and the shear driven parts of this general solution. So maybe a superposition principles is possible. Okay. Now, as I said, I would like to do one last example for pipe flows, which may actually be quite interesting, and it starts with a simple question. Let's consider two pipes, one pipe with a large radius, and then another one with a smaller radius, and then they're kind of somehow they're combined. So I have some sort of mass or volume flux that goes in, some velocity, flow rate of q that goes into these pipes. I have the first pipe here with a diameter of 2 capital D, and then just for simplicity, I say that this one has a diameter of D. So this would be my pipe A, and this would be my pipe B. Now I would like to ask you a question. In which of these two parts, A or B, is the flow more likely to be turbulent? So where is the flow more likely to be turbulent? In A or in B? And of course, now you need to think back a little bit what we said earlier about Reynolds numbers and turbulence. Let's just assume that in pipe flow, the tendency of getting turbulent is directly proportional to the Reynolds number. So, where is the flow more likely to be turbulent?
In A.
Well, let's see what, I don't know, is it? Let's see what you say. A or B? Or the same, who knows? So, of course, the thinking is, okay, where is the Reynolds number higher? And of course, you have a change of flow rate because the diameter changes. But then, of course, you also have the diameter directly in the Reynolds number. I don't know. Okay, so I have now 23 answers. Most of them, 13 say B. Ah, no. Oh, now it changes something. Okay. Well, still, most of you say B with 52% and 42%. Oh no, now it changes. Okay, now it's actually more or less equal, A or B. 42% for A and 46% for B. Let's see. Let's see what the right solution here is. Well, as I said, we need to look at the Reynolds number. And of course, the Reynolds number in a pipe is this Rd that we have defined just a minute ago, which is the bulk velocity, this is written wrongly, UB times the diameter divided by the viscosity. Okay, so the Reynolds number in A would be, of course, UB in A times 2D, you know, so that's the diameter in the first bit, divided by nu. And this becomes Q, so UB is Q divided by pi D squared times 2D divided by nu. So that means in the end, I will get 2Q divided by pi nu times D. That is my Reynolds number in for part A. So it's really just the diameter and the flow rate that you have. Okay. Now let's do the same thing for B. Well, of course, UB comma B times D divided by nu. Okay. Now I calculate again what UB B is. That is Q divided by D divided by 2 squared times pi. Of course, the diameter here is only D. And, well, this is divided by nu. So the result here would be, well, if I go in, it will be 4 times Q divided by pi nu D. So the result shows, I guess that's the important bit here, the Reynolds number is actually proportional to 1 over D of the whole thing. I mean, here it would be in A, well, it's D divided by 2 here, and here it's D divided by 4, and so it's proportional to 1 over the diameter that you have locally. And of course, that makes sense, because in the area, you have a D squared that goes into the velocity, and in the Reynolds number, you just have 1D. So that means at the end of this, we can see that Reynolds B is actually larger than Reynolds A. So that means that B is more likely to be turbulent. Or rather, or I can also say it like that, if you have these combinations of pipes with different radii or different diameters, different cross sections, it's always the one with the lowest cross section that is most that has the highest Reynolds number. And that's something important to keep in mind. The lower the diameter or the lower the cross section is, the higher the Reynolds number is. If you look at a system where you have the same flow rate going through different diameters. So it's always the most dangerous bit is where you have the lowest diameter. That's kind of an important thing to, also from an engineering point, an important thing to keep in mind. So we can say lowest cross-sectional area, most dangerous. Okay. With this, I would now definitely want to leave this area of pipes and channels and so on. And I would like to ask you whether you may have any questions related to these kind of pipes and channels and so on. Okay. Because if not, then I think we can actually move on to the next topic in our course. And the next topic is something that will keep us busy for maybe the next, I don't know, 4 or 5 hours or 6 hours when talking to each other. And that is really the topic of boundary layer flows. Boundary layer flows essentially means we have a flow where we have, which is above one solid wall. And we want to look at the velocity profile adjacent to this one solid wall. And of course, there's different flavors of that. There is, of course, the the spatially developing boundary layers, like the Blasius boundary layer, which we'll talk about quite extensively. There is pressure gradient boundary layers, but there is also parallel boundary layers, like the maybe the Ekman layer, as you have heard about before. But there is also some nice, simple analytical solutions that that people have derived over the years in fluid mechanics, and I guess one of those simple examples I would like to start with now to discuss and discuss with you. So the first example of a boundary layer is something that is called the first Stokes problem. Obviously, it says my internet is bad. Is this bad? Check one thing. Can you hear me?
Yes, now.
Okay, so something went wrong here. I don't know what the problem was. Sorry about that. Well, okay. Anyway, so I need to share again, I guess. So let's go back. So bad network quality. I don't think I have bad network quality. Okay. Okay. Anyway, I think you can hear me again, right? Can you hear me?
Yes.
Okay, very good. Okay, so let's just continue. So the first Stokes problem is the problem that we want to look at. And of course, if there is a first Stokes problem, there's also a second Stokes problem, which we'll look at in a minute. But the first one is kind of one of those first exact solutions that that people have come up with in fluid mechanics as one example of how to use Navier-Stokes equations and calculating exact solutions to the Navier-Stokes equations. This first Stokes problem is also called at times the Rayleigh problem. I guess for us, maybe the first and second Stokes problem has become the most known terminology. Of course, the Stokes problem, that's named after George and Gabriel Stokes, of course. That's the one from the Navier-Stokes equations, and as you know, or as we have discussed before, he lived from 1849 to 1903, so sometimes in the 18th or the 19th century. And then, of course, we have Lord Rayleigh, which, of course, is an important person in fluid mechanics. We will come back to some other aspects that Rayleigh did for fluid mechanics. Actually, he was called John Strutt. Sorry. John Strutt before he became a lord, and he was actually living from 1842 to 1919. And Rayleigh will become very important when we talk about stability. You know, there's a Rayleigh criterion, and there is also, of course, the Rayleigh-Benard convection that we will look at. But both of them, so Stokes and Rayleigh, have worked on this problem, and as I said, it's one example of how to find exact solutions to the Navier-Stokes equation with a very particular way of calculating it. So I would say we can write it like this. It was introduced into fluid mechanics as an example to solve the Navier-Stokes equations in an exact way via what is called a similarity solution, or a similarity transform. This is a very interesting concept, which is actually quite typical for boundary layers, and we will talk about that much more, or about this technique much more. But before we now discuss about the various solutions, let me just start with telling you what the first Stokes problem really is. So it's actually very simple. We consider a flat plate. A flat plate at rest starts to move instantaneously with a velocity capital V at time t being 0. And that means, so if I'm just illustrating that, so we have a flat plate like this. So obviously we have a coordinate system. We can say that this is the vertical direction. We have an x direction. And before, so for time, t lower than 0, the fluid and the wall is at rest. So nothing moves, everything is just steady. But then for time larger equal 0, what we have as what happens is that the wall moves with velocity capital V. And of course, in the way that I introduced the coordinate system here, of course, that would mean that it would move into the positive x direction with the velocity capital V at time being 0. And of course, now the question is, physically speaking, what is happening or what type of solution would one expect? Of course, for time lower than 0, everything is at rest. But then we have this instantaneous change in velocity. And of course, that means that at time being 0, the fluid particles right at the wall, because of the no slip boundary condition, will have a velocity which is V, but then everything else would kind of still have this 0 velocity. So this here would perhaps be the velocity at the velocity profile at t being 0. But then, because we're considering a viscous fluid, or a viscous flow rather, that means that somehow this sharp gradient that we have in the velocity profile, that wants to be diffused away by the action of viscosity. So the adjacent fluid particles, they feel a lot of stress or shear. So that means they essentially, the velocity from the wall, the high velocity of V, diffuses away from the wall. So that means at a later stage, it will look like this, and so on. So this would probably be kind of the velocity profile. And of course, you could imagine that for very long times, I mean, this would look more and more like this. Maybe at some point it would kind of just become vertical. So what we see here is that somehow the wall velocity is diffusing away from the wall into the domain. So we will have kind of an increase, or the velocity profiles would go from this kind of edgy thing into the straight velocity profile as a function of t. Now, what we want to find out now with this the way of solving these equations is how this is going to happen. So we can now write down what physically happens. It's the following: the particles, the fluid particles, close to the wall get or receive momentum from the wall. So due to the no slip condition. And this momentum that they receive from the wall is essentially by the effect of viscosity diffusing upwards into the domain. So, which is diffusing upwards. As I have illustrated here in this figure. Okay, so now how do we do that? How do we solve this problem? Well, obviously it's governed by the Navier-Stokes equations and the continuity equations. So I guess we start by writing them down and seeing what types of terms we can actually neglect. We will use the coordinate system that I have introduced here. So we have the x and the y direction like this. We assume that it's of course 2D. It's a 2D flow. It's fully developed. Yeah, that's it. We start with the continuity equation.
Professor, excuse me.
Yeah.
I have a question. What happens when we have a no viscous flow?
You mean if the viscosity was 0?
Yes. It diffuses with the same mechanism?
No.
Okay.
What would happen? Yes, it's a good question. It's an interesting question. The answer is nothing would happen. Why? Well, the no slip boundary condition, or why do we have a no slip bound? Or let's put it differently. If you had a flow without viscosity, what are the boundary conditions that you have at a wall?
Neumann. Neumann.
No, actually not. Well, let me explain it like this. So, if you have the Euler equation, that means we actually have an equation which is only first order. So there's no second derivative from the viscosity. So that means that actually you only have one boundary condition to fulfill, not two as we have for Navier-Stokes. So that means the correct boundary condition for an inviscid flow, like a potential flow at the wall, is that the flow is not allowed. So if this is the wall, so the only boundary condition is that the flow cannot go through the wall. So that the no penetration boundary condition is still valid. But that means also that the flow can actually have any velocity. So this is not allowed. Okay. So the flow can only go parallel to the wall, but it can have any velocity it wants to have. So there is no slip boundary condition. So that means for an inviscid flow, the speed of the wall actually does not play a role. It will not transfer into the fluid. Even if it did, the velocity of a fluid layer would not affect a fluid layer on top, because there is no viscosity that would give you this this effect. The only way of affecting an inviscid flow is via the continuity. So you cannot compress the flow, and via the pressure. So for instance, if you have an airfoil, you know, something like that, it's not a good airfoil, but you know, you have curvature of the streamlines, and this you can do with Euler equations. So you get a lower pressure and a higher pressure and all of that. But you would not have this momentum diffusion, or rather, as we see later on, the vorticity diffusion.
Okay, thank you.
So the effect of viscosity is actually very important here. Without that, nothing would happen. Okay, so if we start now with the continuity equation, this particular case, well, it's actually quite simple. You know, divergence of u is 0, and the divergence is just du dx plus dv dy plus dw dz being 0. Now, if I'm taking my green pen and I'm taking stuff away, so, well, this guy would go away because we're looking at a 2D problem. So w and ddz is 0. This guy I can also take away because I can say it's a fully developed flow. Fully developed means that this situation is the same also here and here. So, I mean, it's an infinitely long plate, and I move the whole plate at once. There's no beginning, there's no end, there's no difference between this point and that point. Also, there is no external, well, okay, that comes later, but yeah. For the continuity equation, it just means that ddx of the velocity is 0. Okay, that means the only thing that is left, dv dy is 0. This we have seen before many times. And then this together with the boundary condition at the wall, which is the no slip and no penetration boundary condition. Maybe I can be explicit here. No penetration boundary condition. Well, I get v being 0 in the whole domain. That's the first result that we have. V is 0. So everything is only a function. I mean, the only thing that is moving is the u velocity. Okay. Well, now the next equation that we typically look at in these situations would be the x momentum equation. Actually, I could look at the y momentum equations. Well, maybe I can write that down just for completeness. Let's just do that. The y momentum equation. Well, what would the y momentum equation give? It would just give me dp dy being 0. That's it. Because v is 0, so all the other terms essentially disappear. The x momentum equation, well, let me write it down. We have du dt plus u du dx plus v du dy plus w du dz is -1 over rho dp dx plus, now comes the viscous term, nu times d squared u dx squared plus d squared u dy squared plus d squared u dw squared. Okay. What do we need to keep? Or which terms go away? Okay. This one goes away. It's fully developed. ddx is 0. This one goes away because v is 0. This one goes away because, well, it's 2D. And so ddz is 0, w is 0. This one goes away because it's fully developed. This one goes away because it's 2D. Now, what we have always removed before for like channel flow and so on was this term du dt, because we always assumed that the flow was steady. Here, we actually have an unsteady case. So unsteady in a sense as we have seen above, so that we actually have this velocity profile adjusting as a function of time. And of course, that means that we actually need to keep the time derivative in the equations. So that means for the first time,
Professor.
Yeah.
Yeah, I have a question on X momentum equation. The last term is derivative of U over derivative of W, or Z?
Yeah. Yes. Sorry. Yes. That should be said. I'm sorry. Yeah. There is no derivative of. It would be dimensionally completely wrong. Yeah. It's said, of course. Okay. So this is now the first time that we actually have an unsteady term in the equation. So the time derivative needs to be in there, which also is interesting because now for the first time probably we will have a partial differential equation rather than just an ordinary differential equation. So that means that term we need to keep. Then we have the pressure term, dp dx. Now, if we think back, we have always said that the pressure term, so the pressure gradient, needs to be kept if it's a pressure-driven flow, but if it's a shear-driven flow, we can take it away. In this case, as I was saying before, it doesn't matter whether the situation is here, or maybe here, or maybe here, which also means that there is no pressure gradient between those three situations that I have here. So this is clearly a shear-driven flow where this pressure gradient can be removed. So that means in the end, I have the unsteady term and this second derivative. So what remains is du dt is the same as nu times d squared u dy squared. This here is this is what is left from the equations. And of course, if you look at this, you will probably recognize what type of equation that is. This is an unsteady diffusion equation. Well, unsteady because there's a time derivative, and diffusion equation because we have nu times the second derivative of u with respect to y, which is a typical diffusive term. So it's an unsteady diffusion equation, and of course the diffusion here is clearly viscous diffusion. And of course this corresponds exactly to what we said before, kind of our physical intuition. It says that somehow this velocity from the walls, so the change of the velocity, will need to diffuse into the domain on a diffusive timescale with a diffusive mechanism. And that's exactly what comes in. So this partial differential equation, I mean, it is really a partial differential equation because we have a dependence on t and y. It's what is called a parabolic equation, which means that we need initial conditions. So that means initial conditions at time t being 0. And we need boundary conditions. And the boundary conditions, well, essentially are the velocity at the wall. So these conditions, initial and boundary conditions, are as follows: that u as y comma t being 0 is 0. That's my initial condition. And my boundary condition is u at y being 0 and t larger than 0, actually larger equals 0, would be this capital V. That's this no slip boundary conditions. So what we want to do at the end of the day is we want to solve for u as a function of y and t. So this is my unknown quantity that I would like to have as a function of y and as a function of t. Subject to these boundary conditions here. And of course, the solution then should look something like what I have sketched here. Now, I don't think there's any point in trying to start now something at 4 minutes before 6 on how to solve this. I think this is an excellent time to actually close for today. And we will meet again on Thursday at 3 o'clock. And then we go through how to derive or how to calculate this, solution using the similarity method or the similarity transform that that was introduced by Stokes and Rayleigh. So with this, I think we can close for today. Of course, if there's any questions, I'm happy to answer.